In our last lecture, we have seen the concept of arch, buckling, and pre-stress with the help of this wonderful invention bicycle wheel. In this tutorial, we are going to see how these pre-stressing work in steel as well as in concrete element. These are the component of bicycle wheel that we have discussed in detail last lecture. So these spokes are going to act as a pre-stressed column, and this nipple is used to create the tension in these spokes, and this outer rim is acting as a circular arch, and these are connected to tangents to this hub to transfer the torsion into pure tension into the spokes. That's what we have seen in our last lecture. Now in this lecture we will do one commercial software analysis, and we will see how these forces are distributed in these spokes. If you see in this image, the 100 kg load is applied at the hub, and that 100 kg load is distributed to the each spokes by these. Wherever we are seeing the positive value, that all are in tension, and these values are in compression. So as we discussed in our last lecture, so when we apply some loading in the hub, these all spokes not going to get the equal loading because of this one point load, and the spokes which is located very near to the ground at this particular zone going to have maximum load, and all others going to minimum. That to above this central hub, this box going to have tension, and below is going to compression. That's what we discussed. If you see this number also here, these box are getting 20 kg compression, these two box getting 10 kg, and here nearly 1 kg tension. Remaining all other spokes are getting some 4 to 5 kg tension. So if you see this 20 kg load, whether the cross section is 2 mm and the height of this column, let us assume this box as a column and both end is pinned. So this column is a 350 mm height. So how much load it can take before it buckle, that we will see. If you see here, I have taken a column with the two ends are pinned. I have modeled that way. Here and here it is pinned, and 1 kg load is I applied as a axial load here, and for that buckling analysis, the dia is 2 mm and the length is 350, 3 not meter, 350 mm. So for this I am presenting here some first four mode of the buckling analysis. If you see here, there will be one factor is displayed here. What does it mean is, whatever the load we are applying here, multiplying with this factor will give the critical buckling load, Euler buckling load. We might have studied in our theory classes, right? So which means 1 kg I applied here, the factor is 1.3 approximately. So in 1.3 kg it will start buckling for the first mode. If you see the second mode, it's the always the critical mode will be the first mode. If you see the second mode, this is the double curvature buckling. So here it can go up to 5 kg, and the third mode it is triple curvature. Here it can go e power 1 is there, so it can go up to 11 kg. Here it can go up to 20 kg. So the most critical one is the first mode. So these 2 mm spokes of 350 mm length can take maximum 1.3 kg compression only. But if you see in the analysis, it is showing like it is having almost 19.8 kg. Then this definitely it will fail by buckling. But how how it is working in the bicycle wheel? The 2 mm dia spokes are carrying even more than 100 kg of the hub load, that we will see. So, but if there is no for that there will be pre-tension will be there. If there is no pre-tension, then what would be our required dia? That also I have done one more analysis here. 4 mm with 350 mm length, 4 mm diameter I have done. In that I am getting 2 into 10 power 1, so almost 20 kg it can take. So which means the 2 mm diameter spokes is not sufficient to take the load of 20 kg. So it is required a minimum 4 mm diameter. So if we provide 4 mm diameter, we have to dump more steel, as well as not only the it will increase the weight, also these all are aerodynamic effect will be there, so it will increase the drag force also. So instead of that, 2 mm itself it will work fine. So how that is work, that we will see here. For that material, this is just a plate I took actually, but material wise same E350 grade means we will see only these numbers. So for these all are E350 grade spokes I took for the analysis. So the cross section area is 2 mm, and the cross section by way for d square it will give 3.1 mm square cross sectional area. I took the yield strength is minimum is 315 and maximum 355, but we are going to check for the only tension. It's not going to fluctuate, so we can go up to this, but conservatively I took the lesser value 315. For this itself it can take 101 kg even before start yielding. So conservatively I just applied 80 percentage of the calculated value, so it's approximately 80 kg tension is I applied. How this 80 tension applied is, as we discussed, there will be nipple at this part connecting with the rim, so by adjusting these nipples we can create a tension in these each spokes. So now if you see here, this is due to 100 kg load analysis. Here we are getting 20 kg compression, right? So if you see in this diagram, there is 80 kg pretension load is applied here, and another case without pretension here. So because of the applied 80 kg pretension, after there will be some loss will be there. A loss due to small deformation in our outer rim. So because of that, this 80 is the effective load generated in these boxes. Because of this 80 kg pretension is 77.1 kg everywhere. So if you see in this case, what I am is I am just as we discussed in the last lecture, because of the applied 100 kg load here. This is the 100 kg load force distribution diagram. So if you see here, because of 100 kg, originally there is a 20 kg compression maximum in this spot, very near to ground. But if you see here, these all are only due to pre-stress. But as we discussed, all these spokes are will go from the high tension to low tension only because of this vertical load, but it will not going to take any compression. That's what we discussed in our last lecture. If you see this figure, this 77 is the without this 100 kg load. When I apply the 100 kg load, I am getting the force distribution like this. Some spokes are getting tension and some forks are getting compression. These all are compression values. So after superimposing this 100 kg along with the 80 kg pretension, now if you see here, this 77 plus 4 become 81. So because these both are in same sign convention, tension, so it is adding. And if you see this very near to ground, the 77 minus 20 it's become 57. So which means it is coming from high tension to low tension. It is not at all going to near zero or any compression at all. That is how it's work. That is why this bicycle wheel is called a wonderful invention. So even if you apply another 100 kg in this hub, again this may go to 40 kg tension or 30 kg tension only. It will not going to create any compression. That is why the instead of a 4 mm or 6 mm diameter, this 2 mm itself it's working. So the advantage of pre-stress is we can see here clearly. Because of this pre-stressing, the 2 mm spokes itself were carrying the load safely in the location of 4 mm without pre-stressing. Now same way, if you see in the pre-stressed concrete, so there will be a beam which is simply supported between this point, and there is some uniformly distributed load is applied. Because of this load, so at the bottom there will be some tension is created, and the top will be in compression, so there is no reinforcement required. So in RCC, the untensioned conventional rebar, why we will use to provide like this. So in this case, what will happen because of this loading, so it will create the concrete will start increasing the stresses here. So once it's reached the cracking stress, maybe zero point 0.5 megapascal, it will start cracking like this. So this rebar is provided here. So after that, it will take care of that tension. Also, this will go under some deflection as well. Not only cracking, you can see clearly here. It is going some deflection as well here. Let assume this is a 10 deformation and the crack is occurred at maybe 5 megapascal. Still it is carrying the load, it is not collapsing. The problem here in RCC is inside is cracked. So for the deflection criteria, we have to consider the effective cross-sectional area only. Let assume in this area, these are the concrete effective because the remaining portion is cracked. So to meet the codal provision for each element, we will be having certain deflection limits. So to satisfy that limit, we should have the more depth here. So these are the disadvantage in reinforced also due to this cracking, the atmosphere can reach the reinforcement surface, it can make corrosion also, so that will reduce the life of this RCC element. the, in pre-stressed concrete, if you see, as we discussed in the spokes are not taking any, even though it is going to take a 20 kg compression, so we have applied a pre-stress of 80 kg, so that 80 kg becomes 60 kg tension only. So we are keeping in tension, it is not buckling. So 4 mm instead of 4 mm spokes, 2 mm itself working fine, so we are not facing the drag issue at all. Same way here also, to take care of these issues, what we can do is we can provide some tendons at the bottom zone where we are getting the tension like here. And if you provide if you apply some pre-tension here, what will happen, so at in RCC, at originally it will be in flat, and after loading it will go some downward deflection. But in case of pre-stress, whatever the deflection, say example 10 mm deflection we have discussed, right? The same 10 mm deflection we will be applied upward through the eccentric pre-tension like this. Also, we will achieve the whatever the stress we are getting, tensile stress here, let's say example 5 megapascal tension means same 5 megapascal or 6 megapascal compression we will reach through this pre-tension. So the advantage is when we are applying the not only dead load, applying some external load, service load also in service stage, it will come to, this is the full service stage condition, it will come to the flat as like here the non construction stage. Here at the time of construction it will be flat, after loading it will go downward deflection and cracking. But here the construction stage it will be upward deflection, whatever we calculated in the service stage, let's say 10 mm means 10 mm upward deflection, and whatever the tensile stress we are getting here, that will be applied through the pre-tension. So basically here it will come to the flat position. The advantage is here there is no crack at all. Also here it's not cracked. So the to meet the deflection criteria, here we may require more depth. But here since the entire section is effective, so we will require very less depth compared to here. So there is a saving in material. So the same concept what we have seen in the spokes to avoid the compression, we have applied some huge tension. So when we apply some loading, it will come from the high tension to low tension. So it will be in safe and it will not reach any compression at all. Same way, in a concrete, it is opposite to the steel will be good in tension and it will be easily buckle and fail before yielding in compression. In other way, in concrete will be good in compression, so it will be cracked in tension. So what we are doing here, wherever we are getting the tensile stress, we are applying the pre-compression through the pre-stressing. So that pre-compression will be reserved inside the concrete. When we apply some external loading, that pre-compression will get reduced. Like in a steel, the pre-tension is relieved from high tension to low tension. Same way here, high compression to low compression only it's going to happen. It's not going to have any tension at all. So that is how this pre-stressing working in reinforced as well as in the steel element. So we will discuss each this part in detail in maybe separate lecture.